Welcome to Module 1, Introduction to Safety Instrumented Systems. In this module, we will cover SIS components, the difference between SIS and BPCS, protection layers, and key international standards. By the end of this video, you will understand what a Safety Instrumented System, or SIS, is and why it exists. You will also be able to identify its core components, distinguish it from the basic process control system, and understand safety integrity levels. We need safety instrumented systems because process plants handle hazardous materials under extreme conditions. Human operators cannot respond fast enough, and equipment failures can rapidly escalate to catastrophic events. The SIS provides an automated, independent, and reliable solution to detect dangerous conditions and take corrective action. According to IEC 61511, a SIS is an instrumented system used to implement one or more safety instrumented functions, or SIFs. Its purpose is to achieve or maintain a safe state of the process. It must be independent of the basic process control system and engineered to a specific safety integrity level, or SIL. Every safety instrumented function consists of three core components working in series. The sensor detects the dangerous condition. The logic solver decides on the action, based on the input. Finally, the final element acts to achieve the safe state. SIS sensors are the eyes of safety. A key principle is that SIS sensors must be independent from basic process control system sensors. Using separate elements, process connections, and wiring ensures independence and avoids common cause failures, as required by IEC 61511. The SIS logic solver is the brain of safety. Options include safety PLCs, which are certified to IEC 61508, or traditional hardwired relay systems. For SIL2 and above, a safety-certified PLC is typically required to execute the SIFs. SIS final elements are the hands of safety. These devices, like shutdown valves, take physical action. Partial stroke testing, or PST, can verify that a shutdown valve is not stuck, potentially extending proof test intervals, but it does not replace full stroke proof testing. Here is an example of a complete SIF in action. When reactor pressure rises above normal, the sensor detects it. The logic solver evaluates the input and initiates the shutdown. The final element acts, isolating the reactor feed, leading the process to a safe state. The fundamental distinction is that the basic process control system, or BPCS, controls the process and optimizes production within normal operating parameters. The SIS, however, acts as the last automated defense to protect against hazardous events when the process deviates beyond safe limits. This detailed comparison shows the key differences. SIS focuses on safety and risk reduction, while BPCS focuses on control and production efficiency. The SIS must maintain a safe state, while the BPCS maintains the desired operating state. Safety relies on protection layers, often called the onion model. Each independent layer provides defense in depth, reducing risk. The SIS is one of the most critical layers, positioned between basic process control and physical protection. To be credited as an independent protection layer, or IPL, a safeguard must pass the SIDA test. It must be specific to the hazardous event, independent of other layers, dependable with a quantifiable probability of failure on demand, and auditable through regular testing. This chart provides common IPL examples and typical probability of failure on demand values assigned in layers of protection analysis, or LOPA. Remember that these values may vary based on specific corporate risk criteria. Safety integrity level, or SIL, defines the required reliability of a SIF, ranging from 1 to 4. For the process industry, IEC 61511 states that Cell 4 shall not be claimed for a single SIF. Most process SIFs are SIL1 or SIL2. IEC 61508 is the parent standard for the functional safety of electrical, electronic, and programmable electronic safety-related systems across all industries. It defines the overall framework, safety lifecycle, and hardware and software requirements. IEC 61511 is the specific standard for the process sector. It covers the entire SIS lifecycle, from design to decommissioning. This standard references IEC 61508 for device certification and assessment. In addition to IEC 61508 and 61511, Other standards and codes, such as API, NFPA, and ISO, contribute to the ecosystem that supports SIS design, installation, and operation in the process industry. It is essential to know these key terms, including SIF, SIS, and SIL, along with PFD average, RRF, and IPL. These are fundamental to the course content and for certification exams. This slide provides common SIF examples you will encounter in the process industry, such as emergency shutdown, high-pressure protection, and fired heater low-level shutdown. To summarize, a SIS is an independent automated system with three components: sensor, logic solver, and final element. It is governed by IEC 61511 and designed to achieve a specific safety integrity level, or SIL, for risk reduction. This concludes Module 1. We introduced the fundamentals of safety instrumented systems. Next, we will move on to Module 2, Risk Management.